Hello there, Mr. Sutton here, bringing you the BC Calculus Chapter 7 Quiz 3 Review Solutions on Convergence Part 1. For this problem, we're trying to find the convergence or divergence of this series. So we're going to use the nth term test here, and in general, you should always use the nth term test first, because if something diverges by the nth term test, well, you don't have to go any further, and it's a quick test. So to do this test, we just take the limit as n approaches infinity of the nth term of this thing. So limit as n approaches infinity of n to the n over n plus 1 factorial. Now, between these two functions, n to the n is actually the fastest growing function out there. Factorial growth is pretty fast. The only thing faster is n to the n. So because this is a top-heavy function, this is going to go to infinity. Now, since infinity is not 0, in general, whenever you get a number that is not 0 for your nth term limit, a function is said to fail the nth term test and to diverge by this test. For this problem, trying to find the convergence of this series, we're going to start with the nth term test. If we take the limit as n approaches infinity of all this stuff, we're going to forget about these smaller growing terms like 9 and -1, and we're really just left with -3n and 2n, which is going to reduce to just -3 over 2. Now, since this does not equal 0, since our nth term is not going to 0, that means that this function just keeps growing without bound, and we would say that this diverges by the nth term test. To find divergence or convergence on this problem, we're going to use the geometric series test. Now, in general, you should use this test whenever you have a common ratio. So basically, you can rewrite your series as something to the nth power, something that gets multiplied by itself over and over again. In this case, we definitely check to see if it fails the nth term test, but it doesn't. This goes to 0 if you take that limit. In this case, you can rewrite this as -5/6 to the nth power. Whenever you have the same exponent, you can move in division or multiplication to be one exponent. And we see here that this is a geometric test, or geometric series. It has a common ratio of -5/6. The absolute value of that is going to be 5/6, because that's really what we need to look at when we do the geometric series test. If this absolute common ratio is less than 1, which it is in this case, then we would say this is going to converge by the geometric series test. And I'm just going to write converge because I already wrote geometric up here, but that's the test that's going on here. On this problem, trying to find convergence or divergence, we start as always with the nth term test. Limit as n approaches infinity of all this stuff is going to go to 0 because this is a bottom-heavy function. So next up, we're going to try on this one the ratio test. This is a great test to try whenever you have exponentials, factorials, or both in the same problem, any of those. So to find this one, use this one, we're going to take the limit of the absolute value of the n plus 1th term over the nth term. So that's going to be n plus 1 over e to the n plus 1. That whole thing is the n plus 1th term, divided by n over e to the n. And we're going to change flip to simplify this fraction. So in the numerator, I've got an n plus 1 and an e to the n. In the denominator, I have e to the n plus 1 and n. And now we can reduce those exponential terms by subtracting their exponents. So that's going to leave us with just an e in the denominator. Now upstairs, this e to the n is gone. We just have n plus 1. Denominator, we have n times e. As n approaches infinity now, this plus 1 up here can be ignored. So we just have n over ne. N's cancel, leaving us with just 1 over e. Since 1 over e is less than 1, the ratio test unambiguously tells us that our series is going to converge by the ratio test. Now, if this number had been greater than 1, we would say diverged by the ratio test. If this number had been exactly 1, we would say it was inconclusive and we'd have to do more tests. On this problem, to figure out convergence, we're going to use the integral test, which we should use whenever nothing else works and we find that we can integrate the expression. But you should always test the nth term test first, right? So if we take the limit as n approaches infinity, we see this does go to 0. So we have to try other things. Now, before you can use integral test, you need to show that the function is continuous, positive, and decreasing for certain n values. So this is going to be a continuous function as long as we're not taking the ln of 0 or a negative, and also as long as we don't have 0 in the denominator. ln of 1 would be 0, so we don't want n equals 1 here. But if we do n greater than or equal to 3, that should definitely be far enough along to prevent any discontinuities. Function also needs to be positive, which this will be, because you're squaring this term, and really in general, as long as you're not taking the ln of anything less than 1, you'll always get positive numbers out of the ln function. And finally, we want this to be decreasing, which as n keeps going, this function's definitely growing in the denominator, so that means that we're good to go. All right, so now let's take the integral of this thing. The integral test says you need to evaluate the integral that has matching limits of integration. So we need an integral from 3 to infinity of all this stuff. And because we have infinity as one of our limits of integration, we need to write this as an improper integral with a limit in it. So I'm going to use limit as b approaches infinity of 3 to b with all of this stuff inside. And we have a dn now because this is an integral. Now in order to take this antiderivative, I'm going to need to use substitution. I see that I have ln and its derivative n in the same problem. So let me try letting my u value equal ln of n. Derivative of that is going to be du equals 1 over n dn. And then I need to isolate dn so I can replace it later on. So multiply both sides by n. So I have n du equals dn. Now this is a definite integral, so we also need to swap out these n values here for u values. If n equals 3, then that means that u is going to be ln of 3. And if n equals b, then u is going to be ln of b, based off of this u conversion up here. Plugging it all back in, we have the limit as b approaches infinity of the integral from ln of 3 to ln of b. And now we've got, let's see here, this is going to be 7 over n times u squared, 7n actually, because we have a du up here, so 7n du over n times u squared. These n's are going to cancel, and I can rewrite this as 7 times u to the negative 2 just to make it easy to use my reverse power rule on my next step. So bumping this exponent up to a negative 1 and dividing, we have negative 7 u to the negative 1. That's what we're evaluating inside our evaluation box. Still have the limit as b approaches infinity. Still have limits of integration of ln of 3 and ln of b. I'm going to take this negative 7 outside of my evaluation box. And now I've just got, let's see, it's going to be 1 over whatever these limits of integration are. So 1 over ln of b minus 1 over ln of 3. Now as b approaches infinity, this 1 over ln of b is going to go to 0. So I really just have negative 7 times negative 1 over ln of 3, which is just 7 over ln of 3. Since this is a finite number, since our integral converges, that means that our series is going to converge by the integral test. For this next problem, trying to figure out convergence, we first start with the nth term test. As n approaches infinity, this goes to 0, so we have to run more tests. In particular, on this one, we're going to use the p-series test. This is a great test to use whenever you have a single power function or a radical, which you can write with an exponent, in your denominator. So in this case, we see that this is a p-series. It has the format 1 over n to some power. And it has a p-value of 8, that's the exponent down there. Since this is a number that's greater than 1, we would say this converges by the p-series test. And I already wrote p-series here, so I don't have to say by the p-series test. To figure out convergence on this problem, after I try unsuccessfully to take the use the nth term test to disqualify this, because we have a limit of 0 for the nth term on this one, I'm going to go to the p-series test. This is a p-series. I can rewrite this as 1 over n to the 2/3 power. So we have a p-value of 2/3. Since that is a number that's less than or equal to 1, this is going to diverge by the p-series test. For this problem, we're trying to find the radius of convergence. So note on this problem that you can actually rewrite all of this with one exponent, so x minus 2 over 6 to the n. Now, finding the radius of convergence, if you have a geometric series like we do here, then you just need to take the common ratio, the absolute value of the common ratio, so absolute value of x minus 2 over 6, and set that less than 1, and then go from there. And by go from there, I mean basically get it so you have x minus something form inside here. So multiply both sides by 6, and then since I have 1x minus or plus something, my radius of convergence is just going to be whatever number's on the right side here, so 6 in this case. So that's if you have a geometric series. If you do not have a geometric series, then you would basically use the ratio test, get some absolute value less than 1, and do the same exact steps here.